In this video, we're going to talk about the squeeze theorem and then three special limits that can use the squeeze theorem to prove them. So the squeeze theorem says this: if h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing c, except possibly at c itself, and if the limit of h of x and g of x both equal L, then the limit of f of x exists and is also equal to L. So the idea is this: if I have a function f, some point c, and my function, so this is my function f, and my function is squeezed between, or is between two values g, two functions g and h, and furthermore, the limit as x approaches c of g and the limit as x approaches c of h are the same thing. Okay, so this would be like, for example, my g of x, and then down here would be my h of x, and we can see that f is between these two, and the limit of g of x and h of x are both the same, then that forces f of x to also have the same limit. So that's what the squeeze theorem is telling us. The squeeze theorem can be used to prove these three special limits. I'm going to prove the first one here using the squeeze theorem, and then I'm going to leave the second two unproven, but we can prove them basically using the same sort of idea. All right, so the first thing we're going to do to prove the first one is we're going to do some trigonometry. So we're going to take our unit circle. Okay, so this is the unit circle. We're going to exchange this x with a theta here, just to avoid the confusion of the x along the x-axis and the theta being the radian measure of this angle. So we're going to assume theta is the radian measure. So if I just draw this line here, I call this angle theta. Then the idea is going to be this. I'm going to look at the area of the sector of the circle here, and I'm going to squeeze that area between the area of this triangle that goes through these 2 points, and if I draw a perpendicular line here, this triangle here. Okay, so my idea is I'm going to squeeze the area of that sector between these two triangles, and you'll see why this works out in a few minutes. Okay, so first of all, I need the coordinates of these points. Since this point is on the unit circle, and this is the value theta, from trigonometry, we know that the x-coordinate is the cosine of theta, and the y-coordinate is the sine of theta. Okay, so that's the coordinates of this point. This point is actually 1 tangent of theta. Okay, and the reason for that is this line goes through the origin, so it has the form y equals m times x. The slope of this line is rise over run, or y over x. So since this point is on the line, y being the sine of x being the cosine, that means y over x is sine over cosine, which is tangent. So the slope of this line is actually the tangent of theta times x. So we know the x-coordinate of this point is 1 because we drew a perpendicular line here, and therefore the y-coordinate must be the tangent of theta. Okay, so now if we look at the area of the first triangle here, I'll just draw a little picture of it here. The height of this triangle is just the y-coordinate of this point, which is the sine of theta. So remember, area of a triangle is 1/2 the base, which is 1, times the height, which is the sine of theta. Or we can say that that area is the sine of theta over 2. The area of the sector of the circle here Okay. If we remember from trigonometry, the area is 1/2 the angle times the radius. The angle theta is theta, and the radius being 1, we can say that the area of this sector is theta over 2. Okay, and now if we look at the bigger triangle here, okay, this is actually a right triangle. The height of that triangle is the tangent of theta, and the base is 1. So 1/2 the base times the height gives us the area is tangent theta over 2. All right, so we know that the area of this triangle is less than the area of the sector is less than the area of the big triangle. So now we can multiply everything by 2 over the sine of theta. And this is valid on the interval from negative pi over 2 to pi over 2. As long as the sign is positive, we aren't changing the inequality. And that's good because we're looking at the limit as theta approaches 0, which is definitely within this interval. So I can go ahead and multiply everything by 2 over the sine of theta, which is going to give me 1, is less than or equal to theta over the sine theta, is less than or equal to 1 over cosine theta, because tangent is sine over cosine, so the sines will cancel. All right, so now we have theta over sine theta, and we're looking for sine theta over theta, so we can just take reciprocals. When we take the reciprocals, the opposite inequalities become true. So that would mean the cosine of theta, the reciprocal of this, is less than or equal to the reciprocal of this, which is sine theta over theta, which is less than or equal to the reciprocal of 1, which is 1. And now we will apply the squeeze theorem. So if we look at the limit as theta approaches 0 of the cosine of theta, this is equal to 1. If we look at the limit as theta approaches 0 of 1, this is also equal to 1. And since sine theta over theta is squeezed between those, and they have the same limit, that means that the limit as theta approaches 0 of the sine of theta over theta must also equal to 1 by the squeeze theorem. Now I'm going to give you a couple of examples of these using these 3 special limits. So remember, the 3 special limits were the limit as x approaches 0 of the sine of x divided by x is equal to 1. The limit as x approaches 0 of 1 minus the cosine of x over x is equal to 0. And the limit as x approaches 0 of 1 plus x to the 1 over x is equal to e. All right, so for example, if I asked you to find the limit as x approaches 0 of the tangent of x over x. Now, of course, if we just plug in, we get 0 over 0. So we're going to get indeterminate form. So whenever we get indeterminate form, remember, we have to try to rewrite the function so that it is no longer indeterminate form. What I'm going to do here is I'm just going to use some basic trigonometry. I know that the tangent of x is the sine of x over the cosine of x. So I can rewrite this as the limit as x approaches 0 of the sine of x over x times the cosine of x. Then I can split this up into the limit as x approaches 0 of the sine of x over x times the cosine of x. And now this is no longer indeterminate form because according to our first special limit here that we proved, the limit of the sine of x over x as x approaches 0 is 1. And we can see that the limit of the cosine of x, if I plug in the 0, cosine of 0 is 1. So according to our rule that if you take the product, and you're taking the limit of the product, you get the product of the limits. This limit should just be 1 times 1, or 1. Another example of the use of this would be if I asked you to find, let's say, the limit as x approaches 0 of the sine squared of x over x. So again, we could just split this up and call this the limit as x approaches 0 of the sine of x over x times the sine of x. And now again, because the sine of x over x has a limit of 1 as x approaches 0, and the sine of x as x approaches 0 has a limit of 0, the limit of the sine squared of x over x is equal to 0. Let's look at the limit as x approaches 0 of 5 times 1 minus cosine squared x over x. All right, so we have a rule for 1 minus cosine x over x, but not 1 minus cosine squared x. So what we can do here, first of all, the 5 can come out because constants come out of the limit. And we can factor 1 minus cosine squared x into 1 plus cosine x times 1 minus cosine x, and all over x, but we can put the x in the denominator with this one. Okay, so now as x approaches 0, 1 plus cosine x approaches 2, and 1 minus cosine x over x approaches 0, so this limit is equal to 0. One more example. If we take the limit as x approaches 0 of 1 minus the cosine of 3x divided by x. All right, we have a little bit of a problem here because the argument of the cosine function is 3x. But in the denominator, I simply have an x. So if this was 1 minus cosine x over x, I could directly apply my theorem. But since it's the cosine of 3x over x, I can't directly apply it. But what I can do is I can multiply top and bottom of this whole thing by 3. Now when I do that, this 3 in the top I will pull out of the limit. So this is going to be equal to 3 times the limit as x approaches 0 of 1 minus cosine 3x over 3x. Now note that as x approaches 0, 3x also approaches 0. So we can actually kind of make a substitution here instead and say, let's let 3x equal theta, and then when x approaches 0, theta approaches 0. So we could make this substitution and call this theta approaching 0 of 1 minus the cosine of theta divided So that gives you just a few examples of how this theorem can be used.